I think we all agree that Mars is the place to go. And what I'm going to tell you is that for NASA, we also see it as a prime target, and some of the justifications from the science community why we think it is the prime place to go. So in order to say that, I think it's good to start with a big context. And within our universe, where we know that there are a lot of stars, other planets, people talk about a lot about exoplanets, but Mars still is a primordial element in our neighborhood. So in order to understand what Mars it is right now, how it came, it's good to start from the beginning. So we know the Big Bang, 13.7 billion, actually 13.8. And then you start forming all the stars and new galaxies, then stars start to die, and then you come to the present. The key thing is that within the evolution of the universe, our solar system is in the right time, because in order for heavy materials like Jennifer was talking about, like carbon or nitrogen to be formed, you need to start to die, which happens around here. And then in order for a planet to evolve to be like a planet like ours or to Mars, they had to evolve for 4 billion years to be here. So in the whole universe, there are not a lot of solar systems like that have those conditions of have the right elements of heavy components and to be this. So our solar system and Mars, together with it, is a privileged place when you're looking for habitability outside our planet. So this is where our solar system was formed, and I will tell you a bit about the story about the two planets and how they diverge and how we think that Mars may be, why it's so important for habitability beyond our planet. So I always talk about the story about what is important, what are you looking for life, as Jennifer was talking about certain components, where certain things are important. So when you have forming the solar system 4.6 billion years ago, you have the inner part is hotter, then you go away, it gets colder. So this is magic line in the solar system is called a frost line. Anything which goes away the frost line has a lot of water because water was in the ice form. When you go within this frost line, water is very difficult to store in a planet because it's in the gas phase, just a rock. So imagine if you're starting to form planets. All these guys will be devoid in water. All these guys, we have a lot of water. And if you come beyond here, you will see a lot of methane. So if you leave it running for a couple of millions of years, then you end up with our solar system. The magic line still prevails. You have the rocky planets, which are devoid in water. We have trace amounts of water. And then you go here, you have the gas giants, which accumulate all the water in the solar system and all the gases. And if you go beyond the methane line, you start getting all the methane thing. The key thing about this, if you find methane in a place like Pluto, for example, it's great, but it just tells you that it was formed very far away from the solar system, like comets, which is interesting, but it's not beyond that element. When you find a gas like methane or water in a place like this, it's a rare thing. It's something that it was delivered there or something happening on the planet. It should not be there because from primordial conditions, it was devoid from it. And we see our planets as the blue dot. And I think the best analogy that Mars to Earth is when we put all the water out of the surface and make a little bubble. All the water, even below the surface, and on the lakes and everywhere, it just makes this little bubble. So we are still a rocky planet, just like Mars, and all the water is a trace amounts. It just covers a huge amount of our surface, and it drives our climate, our life. So even trace amounts of water in a planet can dramatically change habitability. And that's why when you're looking for water, you don't have to look for a massive amount of reservoir water. Just a trace amount can distort life as we know it. So as I say, where are we going to go? We are in the right place, right solar system. We don't have to go very far from us. So we're going to go to the gas giants. They don't have a surface. So where else do we can go? So let's concentrate on the rocky planets. Those are the guys like us. And then we have Mercury, Venus, and Mars. Where should we go? And obviously, Earth is in the right place. Actually, it's in the right balance of temperature. And it's a little bit anthropocentric definition, but it's the only habitable planet in the whole solar system. And the habitable definition is defined that the surface may maintain liquid water. And we are the only lucky ones. I know it's anthropocentric, but life as we know it is important. All these guys are too hot, this is especially with greenhouse, so we can rule these guys out. So Mars, you say, is out. It's out of the interesting part. But we know that below the surface of Mars, there are enough pressures and temperatures to keep the habitability to the levels that we are accustomed on Earth. And the other interesting thing is that we think maybe in the past Mars was habitable. So those conditions in the past and below the surface are still there. So habitability is an element of Mars which is feasible. And Mars has a lot of other similarities with our planet. That's what makes it a prime target for exploration, for human exploration. It's close and it's so similar to us. Actually, if you look at how long it takes a day on Mars, 24.7. It takes almost the same day as on Earth. It means that diurnal cycles, winds, and a lot of things which are, climatologically speaking, are similar in that sense. The obliquity does change on Mars, but it's now pretty much similar to Earth. It means seasons on Mars have the same contrast between summers and winters and the equinox. It means that having the same seasonal cycles on our planet is also similar for, if you're looking for habitability, those two elements are driving the same seasons and the same diurnal cycles. The thing what makes more different, obviously, the planet is further away from the sun, so it has less sunlight, and it's a smaller planet. Actually, the more dramatic elements is in the atmosphere. As Jennifer was talking about, the main component of the Martian atmosphere is CO2, 95%. In our planet, we're a nitrogen atmosphere and trace amount of CO2, which is growing increasingly, unfortunately. The key thing is that this planet, when you look at the composition, it looks like a pretty dead planet. This is when everything combusted and came to CO2. So, when you're looking for life, when you're looking for habitability, when you look at a planet like this, it doesn't look very habitable in the classical definition. But there may be some surprises. And the story of the two planets actually is so different because of their size. Actually, the planets are, in the planetary evolution, we say size matters. And I will tell you a little bit about the stories about the two. So Mars' radius is roughly half the size of Mars. So when we think about the stories of the two planets, we have these labels. And in our planet, all defined by biology, because biology has been transforming our planet tremendously. On Mars, we can make that, but we can base on geology. The names are complicated, but it just tells you that both planets started and they evolved a lot in the last time. So the key thing is that in the early Earth was a horrible place for habitability. If you are looking for habitable places, Earth was not the place. Actually, it was surface water, heavy bombardment, sporadic geological activity, very irregular. Earth was not a good place to live. Then conditions start to stabilize. You had a regular plate tectonics. Planets start to become a more habitable in that sense. We had an iron-rich ocean, and still no mercury oxygen, and the planet starting to look more like an interesting planet. And then this is the time we think that the conditions were the right place at the right time. Just didn't take a long time. Just a little bit of stability, regular geological activity to drive life to start, microbial life to start. And then for a long time, just this simple microbial life was there. Actually, if you actually send a camera, you wouldn't see it because it just looked like a rock. So for the majority of the history of the planet, life was actually impossible to detect. And it was even not changing the atmosphere, so it was almost impossible. You really had to be an expert to find this type of life. So for 3 billion years, Earth was inhabited by things that we didn't even know how to detect right now. And then this is what we think about life now, which is the multicellular life. Actually, humans are just a little dot of that arrow there. And then life, when it became multicellular, it started to eat more, consume different resources, and then it transformed the atmosphere of our planet into an oxygen-rich atmosphere. So when we typically think about habitability, we are heavily biased to this type of life. And we forget about that there are other types of life that actually are very important and are the precursors for all of this. So this is about Earth. So what was going on Mars during that time? So if you were a space traveler and a time traveler, you actually would like to go to Mars. Because Mars, at that time, when Earth was horrible, Mars was pretty habitable. Actually, this is the time that when we studied geology and history of Mars, is the best time. It's the Noachian. And this is where we have evidence of clay, some probably surface water, big bodies of water on the earlier Mars. And then planets start to change. We have surface volcanic activity, a lot of geological activity happening there. That introduced a global climate change, and then the planets start to change. And it started to die. It was smaller, so it died internally, and it started to die geologically. And when it started to die, the planet changed a lot. So it became, we may think, something like this. So we went from a very habitable place into a place we think we look at right now. It looks like a dead rock in some way. But this is a very simplified idea, and we don't know very well. Actually, we want to send a mission to see if this thing looks like this or more like this. It's still evolving that hypothesis. The key thing about this is this. In our planet, it's very difficult to go back in time from surface because we have plate tectonics, which are great for life because they circulate material. On Mars, never developed that. Actually, it was always irregular geological activity. It means that if you go to the surface right now on Mars, you will find a rock which is 4.5 billion years old, which is impossible in our planet. And that great thing, it means there's a lot of places in that planet that are being preserved for 4.5 billion years. So if you drill a little bit, you may be actually exploring areas which are very habitable. So habitability in the sense of possible life also is good for Earth because there's a lot of resources just below the surface of Mars that trace back to the good old times of Mars. So the question is, was Mars more like this, or was more like this? And it's a big debate in the science community about being Mars wet or Mars warm and wet, about which of the cases is the prevailing case. And there's a lot of debate. It's part of the scientific debate. What are the things? The interesting thing is if Mars was like this, some of the traces will be below the surface, and there are some indications also in the atmosphere. So some of the questions I will be telling you, actually, we have a lot of answers lately about these things. Was Mars ever habitable? How much water did the planet have? And if there are anything below the surface that we can explore as humans going to Mars. So how do we search for life? So as Jennifer was talking about the components, we can look for methane as an indicator for something going on the planet. So totally, methane should not be there. It could come from meteoritic impacts. Comet impact could arrive. You could also have a methane plume here, and below the surface, below some ice, you can have perhaps geology, just simple geology, water, serpentine, and a little bit of temperature, and you produce a gas like methane. Then, And then obviously the most interesting thing, you can also have life. So you can go from a subsurface water reservoir having perhaps biology producing the methane, or maybe geology. And the key thing is that if you find a gas like methane, it's telling you that one of these two things is happening, and maybe this thing is below the surface, which is pretty cool. And it's not highly improbable considering that Mars history, it has been preserved below the surface of Mars. So the idea is that you could that could be connecting with the atmosphere, and you can release methane. So that's one of the hypotheses of how methane could be stored there. And it could point to these two things, which would be pretty cool, because we think the planet is dead geologically and is obviously looking for life. It's interesting. The key thing is methane is not the only one you can look for. Actually, you can look for other things. So if methane in the upper atmosphere, about 60 kilometers, get photolyzed into other things. You can also measure these things. In the lower atmosphere, it gets oxidized with oxygen, and from things like formaldehyde. You can also look for formaldehyde, looking for life. And actually, electrochemistry and other high-energy processes, hydrogen peroxide, we know is there, can destroy methane and produce other things. So methane is a way to look for stuff, for biology, geology. But there are many other processes you can look for that trace back to these good old times of Mars. So we are looking for methane, and we're looking for many others, these molecules, and to see if they're there or not. So the family picture became a little bit bigger now. We have now water, we have methane, methanol, formaldehyde. A lot of these compounds, organic compounds, are very interesting when you're looking for habitability, present and past on the planet. So in 2009, we discovered methane on Mars, and it took us a long time processing the data. It's a very complicated measurement. And we saw these are water plumes, and we saw these very localized plumes of methane, and Gilliker is over there, one of these over there. So we saw a disconnect between the water and the methane plumes, meaning that it was interesting. We know a lot of the morphology of the water cycle drives that morphology that we saw with the water. So those things were very localized. It was very difficult to explain with current physics. We are still trying to mean what it means. But this means that maybe something below the surface on Mars. So when we're thinking about biology, we're not thinking about cows, even though some people talk about them. So we're thinking about radioactive materials, break bonds of water, produce hydrogen, which is free food. You give it to simple archaea, and then with carbon dioxide, you produce a residue like methane. So you go from a very simple process that is prevalent is very prevalent, have seen on Earth, that you can find life this way. So where we think this thing will be. So we have the Photic zone, which is a few centimeters. They have the seasonal cycle, the permafrost, the subpermafrost, and these are all the layers which are very difficult to access with current things. The Photic zone is the radiation place. Anything in this area is very difficult for life. It will get, it's practically in a reasonable amount of time, life will be destroyed, anything we can think of. So habitability has always been defined below the surface. Actually, a lot of the human exploration, when we're thinking about long-term, has been also thought to be below the surface, because it's the place where you go below the Photic zone. So the thing is that some people say that this area is full of ice, actually maybe kilometers deep. You need to go very deep to see water in the liquid form. So the debate, a lot of models about it, we don't know very well. Some people even talk about meters, that this layer moves about up to meters in certain areas. So the key thing is that we know there's subsurface water on Mars. We don't know where. And I think that's kind of the key things of different missions on Mars and other agencies trying to start to probe this area, which is very difficult. Jennifer was talking now. We can drill now a couple of centimeters, and there are hopes to drill a couple of meters, but it's always been a challenge to go below that range. The question is, okay, I tell you that there is methane, maybe habitability, maybe something going on, but was Mars ever habitable? And what do we know about that? So we can do that. We're measuring the two types of water in the atmosphere right now, the hydrogen and the deuterium. So here you have the escape of the molecules. Here the red is the hydrogen, and the more bluish or white is the deuterium. So it's like water and oil. They get differentiated, and you will tend to get the heavy type of water, hydrogen in this case, stored in the atmosphere. So once you break the bonds, you start to lose the hydrogen, and you preserve the deuterium. If you leave that running for billions of years, you will enrich the atmosphere in the deuterium form. So if you measure the D/H, you can actually see how much water was lost. And this is what we did. So the good thing about it is that we have a rock that is from Mars, and it's 4.5 billion years old, and it's actually getting a number which is 1.275 the terrestrial value. Pismo is the Earth in our oceans. It means that the water, primordial water, the water that Mars was at the beginning was the same. It's the same as we have it right now, which is pretty cool. But it tells us that the number was very, very low. Let's say 1 actually is kind of a low number. Interestingly, Curiosity measured a D/H of 3 at 3 billion years old. It means that in a lapse of, let's say, 1.5 billion years, the D/H went from 1 to 3. It heavily increased. It lost a lot of water, and the number got much bigger. So the question is, what is the number right now? So if we know the number right now, we can go back and know how much water was lost. But we don't know. Incredibly, still in the present, we're still debating what is the D/H on our planet, in planet Mars. So we embark in a measurement of that. So let's imagine the number is around 7. So the key thing is that the thermal escape is making this thing getting to be lost, the hydrogen, and then you have the classical water cycle we're going to hear later today, that's moving these two molecules around. The key thing is if you have anything below the atmosphere, below the surface, that hydrogen will store the primordial value, let's say below 2 or around 1. So if something like this happens, you have a connecting place below the surface. Now the D/H now becomes very low. So the D/H has a two-way proxy. It tells you about how much water was lost over time, but also may allow you to see where things are happening below the surface. And I think those are prime places for exploration, for human exploration, and for robotic missions. So we use ground-based telescopes, NIRSPEC, CRIOS, and Seashell. These two are in Hawaii. This is in Chile, to map the D/H of water on Mars. And we published that last year. And actually, when you're looking for an isotopic form of water, you think it's going to be very difficult or kind of hard measurement. But those big bright lines there, these are water, the heavy type of water on Mars. It's very strong water lines because it's so enriched in deuterium that the lines are humongous. You can measure from ground base. And these are the regular water, the red ones here, which is difficult to measure from ground because all our water. You can also measure CO2, which is a way to proxy to the pressure. So what we did for the first time was to get these maps, which is the water maps and the HDO maps. And you can see you can see more water in the north, which is kind of everybody knows about that. It's a northern summer. It releases, not very surprising. But the key thing was this map here, the heavy type of water map. They look very similar, but It's not that similar. So when you make the ratio of the two, you see that the DO rate changes from 1 to 10 across the planet. And what does it tell you that they change so much? Actually, the first time I saw it, I was pretty surprised. I thought this was a proxy to 4.5 billion years old, and it should be the same across the planet. The fact that it was changing so much, I was like, oh my God, I did something wrong with the measurements. So I spent a lot of time trying to make sure that these maps were right. Because if we're so changing, perhaps we're looking at something coming below the surface. As I was telling you, maybe all this area was packed with water from or primordial water. What is going on here? So the data was the data. So I was looking to be a good data set. Actually, Curiosity was making the same measurement over here, and they measure the same value as our map. So it was like, oh my God, this data is actually real. So what does it say? So then I understood that there's a meaning to all this. But just for you to remember, this color here, the greenish or yellowish, is around 7. So what is happening is this. So you have this is a cat, the latitude. You have the equator, the summer pole, maybe some subsurface water on Mars. And you have the polar caps, which is this layer of things. This thing has been deposited millions of years. And the upper little centimeters, they get sublime, actually meters. They get sublime every summer, and they get into the atmosphere, and then they go back in the wintertime. So in the northern summer, this thing comes up, and then you get this 7 value, 7 terrestrial value, the greenish plot that I show you. Then when you go to the winter hemisphere, it gets too cold, and you start to snow the HDO. HDO snows faster than HDO, so it's just as raining water on Mars, no more than that. But it's in the ice form. So it's happening that you see a low DO rate just by climatology speaking. But now we can know that the true number of the atmosphere is around 7. And we also saw some of these patches. We think they come from clouds. And some of them may be related to the thing I was telling you about the subsurface. We're trying to get more data to see if it's true. But I think most of these are related to cloud formations on Mars. The key thing, we got this number 7 there, which is a key. And now we know that the polar cap, which is the main reservoir of water on Mars, now has a DO rate of 8 terrestrial. And it's a very enriched number. And you say, well, what is the great thing about having that the number is 8? Well, it has a pretty important significance, actually. So if you put it back in time, you know that the number in the atmosphere is around 7, and the polar water is around 8. We have the water from meteorites around 1. So you see that the water, the DO rate has been going like crazy over times. As Jennifer showed, Curiosity now measures around 3, so we have a midpoint there. We have some other meteorites. So we see that the DO rate changed a lot. And then we don't have a lot of middle points. But the key thing is that Mars, you can put them all between them. Mars was increasing the DO rate a lot. And what does it tell you about? What is the DO rate actually telling you anything about the water on Mars? Well, it's a very simple relationship between the red trace and the blue trace. And what is the blue trace? It's a relationship, how much water is right now on Mars and how much water was in the past. It's actually a simple formula. You can use that formula to calculate the blue. And we know that in the past, Mars had 6.5 times the water it has today. The good thing about it is that we know a lot about the water on Mars and the inventory of water on Mars. So we actually know very well. So we can multiply that number by 6.5, and we can know exactly at every time of the history of Mars how much water was there. It's an approximation, but it's a pretty good approximation for the history of water on Mars. So it means that Mars was a very habitable place, but it lost 87% of its water. So what we did, we just got the polar cap. We know the amount of water. We multiply by 6.5, we melt it, and we see where it went. And it produced a huge ocean on Mars. We covered 20% of the planet. That explains some of the morphologies that have been observed on the planet. Over time, that ocean has been receding. The water has been escaping. Some of them got percolating below the surface, but a lot of the water has been escaping. And then the planet became the red planets as we know it right now. But the key thing is that Mars was actually a pretty habitable planet in the past. We have a lot of evidence, and this is another evidence that tells that Mars had a big ocean covering 20% of the planet's surface in the beginning. Maybe even more habitable than our planet at that time. So how we can actually say about beyond what I would just show you? The cool thing is that the DO rate is actually can be defined as a low limit. There's probably more water in the past. because you need the water to be escaping or be stored in some way. There may be more water below the surface that doesn't go through the escape process. So this is like a low boundary, how much water in the past. And it's already a lot of water. So I told you that the water now is stored in the polar caps. In order for the water to escape and enrich in the deuterium, it has to be volatile. So it has to go from the polar caps into the atmosphere and then back and forth. And Mars has doesn't have a moon like our planet, so it means that the obliquity changes like a lot. That means that the planet is subliming the polar caps all the time. Actually, every 5 million, 3 million, we know that the polar cap is going to go away. So the lifetime of the polar cap is very short compared to the 4,500 millions of years of the lifetime of the planet. The big question has been, is all that water has been frozen or liquid? And it's actually counts. People fight about it and say, no, it was liquid, no, it was frozen. So there was a nice paper just came out recently last month saying that there's a midpoint between the two and saying there's a model explains that water was maybe liquid for millions of years, and then it was frozen for a long time, and then liquid for a long time, for millions of years. So it's like an iteration process. But there was a time for millions of years Mars was covered in a lot of water, and some of the water percolated below the surface. Interestingly, the map that I showed you with the coastlines and all those things, well, actually maps some of the other morphologies. You can actually look at the craters and the shape of the Martian surface, and you can actually create a coastline. And the DORH map that we got actually matches pretty nicely. So there's a strong evidence now that there was a big ocean on Mars. So what are the next steps? So from the space missions, the next things we're trying to do is we have the ExoMars mission that just launched 2016. Next month, we are arriving to Mars, going to get the first map of methane and water. Probably going to settle the debate about methane. It's going to be pretty cool. The Mars rover was supposed to land in 2018, but it got delayed. It's going to be 2020. And so I was in Germany when I did my PhD, and I was involved in the ExoMars rover mission. And every time I go to the meeting, it started like 20 years ago. They were thinking about doing a drill, and it was 20 meters. Every time I go to the meetings, 1 meter less, 19, 18. The last time was was like 5 years ago. It was 5 meters. Hopefully. No joke. I think they're gonna do 2 meters now. That's the prevailing view. And it got delayed to 2020 because they're still struggling to drill 2 meters. But you got to understand, drilling is not easy, but it will open a complete new avenue of exploration on the planet. And I'm excited also about this. This is going to be the first time we can actually measure the atmosphere of Mars. We have the James Webb, which is an asset mainly for astrophysics, but it's good for us because it's going to be the first time we can actually map the planet above our own atmosphere, high quality, and get the first maps of water, deuterium, and methane on Mars with James Webb. And then with the Mars 2020, which is a continuation of the Curiosity. So the conclusions are, the first map of water reveals strong isotropies, and that means that there's a lot of loss on the planet and maybe something below the surface. We need to understand more about that. That will mean that there was a big ocean on the planet, maybe bigger than our Arctic Ocean, and maybe more water in the past. So the question has been that how long that water was there, and I think all of us are agreeing that for at least millions of years, the planet was covered with water on Mars. So from the robotic exploration, we're trying to get more mapping to see if we can actually pinpoint any place which is habitable. And then it will assist with the human exploration beyond the robotic to go for the most interesting places on the planet. So that's all. Thank you. Yeah, sure.
Any questions?
Yeah.
Hi. So I was curious as to whether or not you could apply that type of approximation you used for the water inventory, the original water inventory. Could you apply that to the original inventory of CO2 that was on the planet as an approximation as to how thick the atmosphere may have been?
Yeah, that's a good point. So the question is how we can have a pretty good idea about the hydrogen escape, because the dichotomy between the mass of hydrogen and deuterium is so big that the escape is much more notorious, we can say. And it means that you're looking actually for the hydrogen escape. When you're looking for CO2, carbon and oxygen, the isotopic forms are much more subtle. So the escape rates are very similar. It's very difficult to make the same approximation with the organic. People do it, but the best actually way to do to go back with the carbon dioxide is to look at the argon and other heavy radioactive elements and see how the ratios are, and infer that way. Well, I mean, it's one of the big goals of Methane, and Methane has been doing a lot of investigations. But as I say, for hydrogen, it's a little bit easier because of the economy is higher, the escape rates. For the heavy molecules, atoms, it becomes a bit more tricky, and that's why it's more modeling involved in that.